Yeah, good morning. First of all, any questions about what was discussed in the previous lectures? Okay, so basically, then I'll continue with discussion of critical phenomena. Critical phenomena basically tells you, is concerned with basically the behavior near a continuous phase transition. And last time we saw that there are many quantities that show singular behavior near a continuous phase transition. And that singular behavior was characterized by critical exponents and things like that. And I also told you that there are many systems which apparently are very different, where basic microscopic physics could be very different, but near a critical point, they show very similar behavior. And that concept was known as universality, where I told you about, there are these classes of systems, and each class, there would be several different systems, and their microscopic physics, Hamiltonian, etc., are quite different. But still, if they, when they come close to a critical point, the singular behavior, which is characterized by these exponents, they turn out to be the same. So this is a very sort of interesting and sort of peculiar phenomena. But one of the things that one would like to understand is why all these different systems with different microscopic physics are behaving in a similar way near a critical point. So that's something that I'd like to go into a little bit. So as I said, there are only a few parameters which are called relevant in this particular context, like the symmetry of the order parameter, space dimension, range of interactions, and so on, which are relevant in the sense that determine the value of the critical exponents. And there are different systems for which these things are the same, but many other things can be different, but they will still show the same critical behavior. And that is what we are talking about when we talk about universality. And understanding of this universality basically comes from the fact, and this is something that I want to sort of emphasize and spend some time on, the fact that there is a length scale in the problem, characteristic length scale in the problem, which actually diverges at the critical point. And since one is talking about the critical behavior is governed by fluctuations at very long length scales, and so they are somehow insensitive to what happens at the very particle level, short length scales. So basically, the reason that one has for this universal behavior is that there is a correlation length in the problem. Correlation, I will define it in just a moment, and that actually diverges at the critical point. And then that says that when one is looking at long wavelength behavior, then that will not be very sensitive to what happens at the microscopic or particle level scale. So different models may have very different characteristics at the particle level, but at the long wavelength limit, since at the critical point there is this length scale which becomes infinity, they basically show the same critical behavior. So how do we define this correlation length? So I'm sure you're familiar with the idea of a correlation function. You have these fluctuating quantities, spins or densities and things like that. And then you look at how the behavior near one point in space is correlated with the behavior at some other point in space. So that is basically what the correlation function measures. So basically, for the case of this Ising model that I have mentioned many times, where you have this variable sigma, which take on values plus or minus 1, and these variables are sitting at lattice sites. So one is looking at the correlation between the spin at lattice site I with the spin at lattice site j. And typically one sort of subtracts out the product of the two averages. And this is how one defines a spin-spin correlation function now, which will depend on the distance between site I and site j. So I've called this R as the distance between site I and site j. And so one wants to find out how this correlation function behaves as a function of R. As you go to larger R, how does it fall off? Eventually, one expects that, if I look at 2 points which are very much separated in space, then the spins at those 2 points will not be correlated. So one expects this function to go to 0 when R becomes infinity. The question is, how does it go to 0? Does it go to 0 as a power law? Does it go to 0 as an exponential? And things like that. So in critical phenomena, one finds that this correlation function actually has a power law part. D is a spatial dimension. eta is another critical exponent. I mean, I've told you about alpha, beta, gamma, delta. This eta is another critical exponent that tells you about the power of this prefactor. Where more importantly, it falls up exponentially over a length scale, which is this correlation length that I told you about. So the correlation will go to 0 as r goes to infinity. And there is a length scale that tells you about how fast it goes to 0 as you increase r. And the behavior that you see at a length scale which is much bigger than this correlation length will be different from the behavior that you see length scales which are much shorter than this correlation length. So the problem has a characteristic length scale, and that is something that is very important. So near the critical point, this length scale becomes very large, and it diverges at the critical point. So this is actually a characteristic of second order or continuous phase transitions, that at the critical point, there is a length scale which goes to infinity. And how does it go to infinity? It goes to infinity with an exponent which is called nu exponent. So in addition to this alpha, beta, gamma, delta, I have introduced now two other exponents. One is this eta that tells you about this form of the power law, and exponent nu that tells you about how the correlation length actually diverges as you approach the critical point. Critical point by definition is little t equal to 0. Little t, if you remember, is t minus tc divided by tc. So when T is equal to Tc, temperature is equal to the critical temperature, little t goes to 0. So that says that the correlation length diverges. And as I told you, this 2D Ising model, there is an exact solution. And there the values of all these exponents are known. You don't have to remember these values. But the point is one can define these exponents in this case where one has an exact solution. And there one finds that these values are actually not, these are typically ratios of two small numbers. Why is it so is something that nobody knows. But these numbers basically define this universality class. All systems for which these numbers are the same belong to the same universality class. They can have very different microscopic behavior, but that doesn't matter when one is looking at critical behavior, because there is a length scale which is diverging at the critical point. And so if you look at quantities which basically are characterized by lengths much smaller than the critical this correlation length, those things don't matter. Okay, so one thing that you can easily see from here is that when this xi goes to infinity at the critical point, correlation fall off as a power law. So people say that system at the critical point is scale invariant. Whenever there is a finite xi, as I said, behavior at length scales much smaller than xi and much bigger than xi will be different. So there is a characteristic length scale. But when the xi goes to infinity, correlation is just a power law. So this is another property of the property of the critical point, which must be clear from this particular form, is that at the critical point, the system is scale invariant. And this is one of the ideas that go into this formulation of scaling theory or renormalization group theory that hopefully I'll go, at least the beginning of that I'll get to in the next lecture that I'm giving later today. But this is a very important fact that you should keep in mind, that correlation length actually diverges. That leads to universality. Okay, so one more thing that I want to point out. And so this is something that I've already told you about. These universality classes are important also in non-equilibrium physics. So new thing is this. I have defined these 6 exponents. Alpha, beta, gamma, delta, these are from equilibrium behavior. And this eta and nu, these are from correlation length, correlation function. All these exponents are not independent. There are these specific relationships among these exponents, which is, this relation is satisfied for all critical points. These are very general. It doesn't matter whether you're looking at Ising model or you're looking at binary liquids, looking at superconductor, superfluid, whatever. So this alpha comes from specific heat, beta comes from order parameter, gamma comes from susceptibility, and nu comes from correlation length exponent, and then there is eta, is basically comes from the power or the power law decay that you have at the critical point. And one finds that these relationships are always satisfied. And one of the things that, when one is trying to sort of study an unknown system and then does some simulations or experiments or whatever, from which one calculates these exponents, a very sure test of whether you have done the calculation or experiment correctly is that whether your exponents satisfy these conditions. So where do these conditions come from? So that is where actually people were worrying about it for a long time when they knew that these conditions exist. And they came up with something which is called a scaling theory, a scaling description, which is phenomenological at this point. That given these results, how can you sort of formulate a theory which will give you these results? And this theory is not coming from some microscopes or whatever. One theory is coming from some ansatz, scaling ansatz or assumption, such that that assumption will lead to these relationships among the critical exponents. And just mentioned renormalization group theory, that gives you actually a calculation of this scaling functions. But when it was first proposed, there was no calculation of the scaling functions, except for 2D Ising model and things like that, where things are known exactly. There was no calculation, but just from looking at these relationships, people found that if we make some assumption about the behavior of the free energy, for example, that will lead to these scaling relations. And then the task then becomes finding the scaling functions. So what is the scaling hypothesis or answers? So one is looking at here, talking about equilibrium problems. So one is looking at free energy, and one is looking at the singular part of the free energy. Because I mean, you know that by taking derivatives of the free energy with respect to temperature or with respect to magnetic field and things like that, one can generate the thermodynamic quantities.
When 2 minutes explaining to people what is scaling, and there will be people who know.
Yeah. That I mean, how this comes from a scale transformation and things like that, that will be the subject of the lecture that I have later today. But at this level, this is purely an ansatz, phenomenological. That for a magnetic system, you have this reduced temperature and you have a dimensionless magnetic field. These are the important variables. So your free energy will be a function of these two variables. And one assumes that this dependence of this quantity on this T and N is given by a function that looks like this. So there is two unknowns here. There is an exponent lambda1 here and the exponent lambda2 there. And of course, this function is unknown. There is a scaling function. But the argument is that if we assume this particular form, then these exponent relationships will be satisfied. Yeah? And it's very easy to see why that is so, because if you know the singular part of the free energy, then take a derivative with respect to temperature, then you generate some internal energy, take two derivatives, you will get specific heat. If I take a derivative of this with respect to H, then I'll get the magnetization. I take two derivatives, so I'll get the magnetic susceptibility, etc. So the exponents alpha, beta, gamma, delta, etc., which tell you about the singular behavior of these quantities, specific heat, susceptibility, magnetization, can be related to these two exponents lambda1 and lambda2. Just by taking appropriate derivatives of this, you generate the various thermodynamic functions. No, these are constants. Lambda1 and lambda2 are just two constants. At this point, we don't know what they are. So that connection of this lambda1 and lambda2 with these exponents, to get that, you have to look at derivatives of this to get, let's say, the specific heat. Specific heat exponent is alpha. So then you write alpha in terms of lambda1 and lambda2. Similarly, beta you write in terms of lambda1 and lambda2, and gamma also you can write. And there are only two, so alpha, beta, gamma will not be independent. And this exponent relationships will follow from how this alpha, beta, gamma depends on lambda1 and lambda2. Yeah? So this is what is done here. Since time is a little short, I will not go through all the algebra, but you can see here that one is taking derivatives of this free energy with respect to temperature or magnetic field, or one derivative or two derivatives and things like that, that we generate the thermodynamic functions, and you relate this lambda1 and lambda2 to the other exponents that I had defined earlier. And it's a good exercise to show that these relationships that I had written down earlier will be satisfied for arbitrary values of lambda1 and lambda2. But your critical exponents for the particular system that you're looking at will be dependent on lambda1 and lambda2. So if you know the exponents, from that you can get lambda1 and lambda2. A priori, you don't know what this lambda1 and lambda2 is. But these relationships that I have told you about, the relationships among the critical exponents, they will be satisfied irrespective of what values lambda 1 and lambda 2 have. But for a specific system, since these values are related to alpha, beta, gamma, delta, if you know the exponents from that, you can calculate what is lambda 1 and lambda 2. Yeah, is that? So just a consequence of this is that, I mean, this is what we wrote down. Singular part depends on reduced temperature magnetic field, and we call this lambda 1 and call this lambda 2, but now we have written lambda 1 and lambda 2 in terms of the actual critical exponents. So if we now accept that, then, for example, if I want to look at the magnetization, that will be a first derivative of this free energy with respect to magnetic field. First derivative will bring down a factor of t to the delta, so t to the minus delta, and then you will have the derivative of this function, t plus minus. Oh, one more thing. When you are talking about plus or minus, the plus refers to above Tc and the minus refers to below Tc. The scaling functions need not be the same as you are approaching the critical point from above or below. But anyway, that doesn't matter for what I'm talking about here. So this implies the magnetization will depend on temperature and magnetic field in this particular way. Now, what does this form imply? That if I take this quantity to the other side, we will have m divided by t raised to the power beta will be a function of h divided by t raised to the power beta plus gamma. And so this is something which is very useful because you see, experimentally, for example, if I'm dealing with a magnetic system, one would measure things as a function of temperature, which will change this little t, or one would measure as a function of magnetic field. So one can make any number of measurements. But all these measurements can be put onto a single curve if I plot this quantity versus that quantity, if you choose the values of beta and gamma properly. So this is a way of determining what are the values of the exponents. So if you're dealing with some unknown system, you do these measurements, just isotherms, particular magnetic field, you measure many different temperatures which go through the critical point, change the magnetic field, do the same measurement. So you'll have many, many curves. But scaling theory tells you that if I look at this ratio versus that ratio with appropriate choice of beta and gamma, then all these curves will collapse onto a master curve. One will get a master curve, two master curves, because one is for t bigger than Tc and one is for t less than Tc. So this is something that people use very, very commonly to calculate the critical exponents, either from simulation data or from experimental data. What are the values of beta and gamma for which you will get this scaling collapse? And I'll just show you very quickly this is an very old result. As I said, the scaling behavior was known earlier as a sort of ansatz, and this renormalization group framework that gave you a sort of theoretical way of deriving this scaling behavior. But at this point, the scaling behavior was just basically saying that if you assume this, then you get that. But you see that this is for a magnetic system, and you see that there are many measurements. For t bigger than Tc, there are so many temperatures that people have looked at. T less than Tc, so many temperatures experimenters looked at. Each temperature, you change the magnetic field and look at how the magnetization depends on both the magnetic field and the temperature. The point is, if I plot this combination that I have just shown in the previous slide against that combination, then all these data points will fall on the same curve. And this is quite remarkable, I think, that you are looking at data taken at some 20 different temperatures and many different magnetic fields, but with the appropriate choice of the critical exponents. So this is, again, another very important and very, very interesting property of systems near the critical point, that the scaling description seems to work. And so one of the things that people were worrying about is how to derive that scaling description from some theory. And this is what we'll be coming to later on. Okay, so all these things are basically yeah. So again, going back to this is basically the scaling hypothesis, that I measure m as a function of temperature and magnetic field, and so that's all I do. I mean, data that I showed, different temperatures as a function of magnetic field. So at each temperature, you will get a dependence of m on h as you are varying h. And you will have so many curves. I mean, if I have 20 different temperatures, then you will have 20 curves, which will tell you about how m depends on h for each of these temperatures. And then yes. Finite size, there is one more variable that you have to take into account, which is the size of the system. But if you include that in your description, then there is something called finite size scaling, which says that similar data collapse can be obtained also as a function of system size. So we have to, I mean, if you want to do that kind of scaling, then you have to have the results for many different system sizes. And again, data for all of those system sizes, you can collapse onto a master curve if one does appropriate scaling. But here one is doing experiments. So typically, I mean, one assumes that this is in the thermodynamic limit. System size doesn't come into the picture. The two variables that are important are the temperature and the magnetic field. And as I said, in this picture, you have so many temperatures and so many temperatures here, T less than Tc and T bigger than Tc. At each temperature, one measures magnetization as a function of magnetic field. So you will have, I don't know, about 15 temperatures, and at each temperature you have a curve. This temperature, if I plot the magnetization as a function of magnetic field, I'll get a curve. So you have 15 curves. Now the point is, if I choose this exponent, beta, the value is given here, gamma is given, and beta is given. If you now, instead of plotting m versus h, if I plot this combination versus that combination with appropriate choice of the exponents beta and gamma, then you should be able to collapse all these 15 different curves onto the same master curve. And it does happen. I mean, you can see that there are many data points. So there is one curve for t bigger than Tc and one curve for t less than Tc. As I said, this scaling function, g plus minus, plus could be different from g minus. So there are two different functions. But the point is, if you look at all the data for t bigger than Tc and all the data for t less than Tc, all of them can be collapsed onto a master curve when you choose this exponents properly. Yeah. So the purpose of theory now is to determine these exponents and the scaling functions. So the problem has been reduced to this. That the free energy or the singular part of the free energy will depend on temperature and magnetic field in this particular way, where the alpha and delta are exponents which we don't know at this point. So you have to calculate those from theory, starting from microscopics, and the scaling functions, g plus minus. If you know, then if you can do that, then basically you have solved the problem. Then you can compare what you get with experiments or simulations or whatever. Yeah. Okay, so this is the theoretical, this is the problem that people tried to address. And some breakthrough was done in the 70s. Ken Wilson got a Nobel Prize for the development of a theoretical framework in which one can actually do this calculation, can get the critical exponents, scaling functions, etc., starting from a microscopic Hamiltonian. So the remaining, hour or so that I have, including this and the next lecture, I will try to tell you about the theoretical development.
Maybe 2 words on Kadanoff and Fisher.
Yeah. So Kadanoff will appear very prominently. And yeah, Michael Fisher worked, of course, they were the same university, Michael Fisher and Ken Wilson. They actually had a lot of discussion with each other when this theory was being developed. And people were a little surprised that Fisher didn't get the Nobel Prize, only Wilson got the Nobel Prize. But then, the argument was that if you give to Wilson and Fisher, then you also have to give it to Kadanoff. And you cannot give to 3 people. So only Ken Wilson, who is actually, his papers are single author papers. The Renormalization group paper that initially were published only by Ken Wilson. So this we have done. Let me not. So now we are going to the theory part.
Would you like to start on the next part, or shall we just break for tea and then?
So I think about 10 minutes on the Landau theory, and then going beyond that, I can do in the last lecture.
Maybe a little less.
Okay.
Yeah.
So I'll just show some pictures. So what is the theory? The theory is many different theories that people have done, but the one that will connect easily with RG, renormalization group, is this Landau-Ginzburg kind of description, where the starting point is basically writing down a free energy, which is a functional of this field. Phi of x is a field that represents the kind of order the system is developing. So phi average is the order parameter. And order parameter is 0 above Tc, and then it takes on some finite value for t less than Tc. So assume that you know what the order parameter is, and there is a field. Field basically is something which varies in space and time that corresponds to that order parameter. And what Landau told us is that the free energy can be written as a functional of this field. And here we are looking at a field which is just a scalar. Talking about, let's say, the Ising model, order parameter is a scalar. So the field itself is just a number, but number is now allowed to vary in space. And you are writing free energy. At this point, this free energy is based only on symmetry. Another thing that is very important in studies of phase transitions. So free energy has to be invariant under the appropriate symmetry. So in the Ising model, the symmetry is phi going to minus phi, sigma going to minus sigma. So all the terms that will occur here will have even powers. You cannot have odd powers here. And that's very important, that once you've identified the order parameter, then you also have to look at the symmetry of the problem. And you should keep in this free energy all terms which are allowed by symmetry. So that's what one has done. I mean, one has written phi squared. You cannot have a term which is linear in phi, because that will change. If you make phi going to minus phi, then any odd power of phi will change sign. And that is not allowed, so only even powers. And then if you allow this phi to vary in space, then there would be derivative terms and so on. And I have stopped here. The fourth order term, there could, I mean, in principle, there would be sixth order term, eighth order term, etc., etc. But the physics will not depend on that. And that is another thing that one gets from RG, that you can have these higher order terms, but those are not relevant for calculating critical behavior. So this is basically the starting point, Landau theory, that given the phase transition that you want to describe, first of all, you have to basically understand what the order parameter is. And when you know that, then you construct this free energy functional, keeping all terms which are allowed by symmetry. And here, something that is invariant under phi going to minus phi will allow only even powers. And you just keep the terms which are also derivative terms and the lowest order terms and so on. So if you have this, the next step is very simple. You can do a very simple theory saying that this phi doesn't have any spatial dependence. This phi is the same at every point. And that assumption is called mean field theory, that you throw out all spatial fluctuations, spatial dependence of this order parameter field. If you do that, then this term goes to 0, and you have a phi average squared here, and phi average to the power 4th here, and then you find the value of phi average, which minimizes that. So this is just very, very simple calculations. Once you have this particular form of the free energy functional, mean field theory, you assume that it doesn't depend on space. Its value everywhere on space is equal to this order parameter. And as a result, you get this free energy depends on only phi average squared and phi average to the 4th. And then if you want to plot this as a function of phi average, then you will get different curves. And the important thing is that here, this R parameter changes sign at some Tc. Depending on whether R is positive or negative, you will get either this kind of a curve, which has only a minimum at phi average equal to 0, or if T is less than Tc, then you will have this minimum will become a maximum, and you will have a double minimum curve. And this is what the phase transition is all about. That above Tc, your order parameter is equal to 0. But this theory tells you that for T less than Tc, the minimum will not occur at 0, but will occur at some point which is a little bit away from 0. And so you'll have a finite value of the order parameter. But this value can be positive or negative. There is no distinction between this minimum and that minimum. System can go into either one of them. So again, this is what you would expect, that Ising model, the spontaneous magnetization can be positive or negative. Both of them are allowed. And as a result, this theory then will tell you that as you keep on changing your temperature so that this R, the coefficient of the quadratic term, goes to 0, that point is the critical point. And if your temperature is above that, then we'll have m equals 0. And if you have below that, then m will have a finite value. So at this very simple level, one can have a theory of what is going on. And once you accept that the free energy is given by this, you calculate this phi as a function of temperature and all that. From that, you can also get the critical exponent. So there will be some mean field values also of this critical exponent, alpha, beta, gamma, delta that I told you about. The whole theory can be worked out with this assumption that phi doesn't depend on the position. So, this theory is so simple that, once you know the free energy functional, it's kind of trivial to work it out, and everything can be obtained. But the unfortunate thing is that this doesn't give the right results. That mean field theory, this simple version of the theory, will give you critical exponents that are different from what one finds from other sort of more accurate calculations. So that is the main problem. That is the problem is that, and how to go beyond mean field theory. Mean field theory is just writing down the free energy on the basis of symmetry, then assuming that the order parameter field doesn't depend on space, and then minimize the free energy with respect to this value of the order parameter field, and then try to find out whether there is a critical temperature such that above this, the order parameter is 0, and below that, there is a non-zero value of the order parameter. And then you can calculate everything that you want, all the thermodynamic functions, you can calculate the critical exponents and so on, but comparison with actual results show that it doesn't work. So the next lecture, whatever time I have, I'll give you some indication of how this more sophisticated theory is developed, which gives rise to the correct values or correct description near the critical point.
That is also today, so that we
and that's, yeah.
Today
That's okay.